Here's a problem that involves conservation of energy and work due to friction. Looks like this. There's a big orange box here, and we'll give the box the mass m here. And it gets itself pushed up against a spring here, and say the spring has a spring constant k, pushed up against the spring. And it gets pushed against the spring by a distance delta x. So you can imagine the mass is here, and someone pushes it back a distance delta s against the spring and holds it. So what they're going to do then is when they're holding here, they're going to release the box. The box is going to be pushed by the spring, or alternatively the stored potential energy of the spring is going to go into kinetic of the box. The whole thing is going to fly this way, like that way. It's going to fly across this frictionless surface. Not fly across, but slide across the frictionless surface. It's going to hit this friction here. And of course what friction does is sucks the energy out of things and causes things to slow down and I suppose eventually stop. So what we'll see is we'll see this box here, the orange box will be sitting over here at rest, because now stopped now against the friction, and it's moved a distance delta d along the friction. So what we'd like to know is what is delta d? How far along the frictional surface is it going to slide before it stops? So I see this sort of as a system that looks like this here. I'll say my E initial is equal to E final, but we have some additional work done due to friction here, and if you sort of follow along in the class, I'm going to call this the sort of the barbecue theorem here, because I'm going to say I have some initial energy of the spring, of the box and the spring, all the mechanical energy. I'll have some final energy of all those things, but I'm going to have some work due to friction done, and I know this work due to friction is going to be done because this area of the friction right here is now going to be heated up. I showed you some images in class there where we know as the box slides along the surface here, there's going to be sort of a net outwards loss of mechanical energy in here. This is the work due to friction. So this arrow here indicates the energy leaving the mechanical energy the box would have had. So the surface is going to be warm, and I have to account for that with my work due to friction right here. So if I just start filling things in here, the initial energy I see is the 1/2 k times delta s squared. That's the spring all compressed up. And when I'm sort of done, when I see the box sitting here, it's not moving, so it doesn't have any kinetic energy. It didn't go up or down a hill. It has the same vertical level, so no potential energy either. So this final mechanical energy is just going to be zero, but I will have some work due to friction done. And the work due to friction here is the frictional force times the distance over the surface that it slid. And this is in fact what I want to solve for here. So I think the solution is kind of apparent now. 1/2 k delta x s squared, that's the initial potential energy of the spring. All that's going to go and do this frictional force here, and I know the frictional force for an object on a flat surface is just mu times the normal, and the normal force is going to be m times g, and you can put a delta d in there as well. So I think here's the solution at hand here. Let's just summarize it one more time, wrap it up. Here's the initial potential energy of the spring right here. So this is like potential energy of the spring, because initially the box is all pushed up against the spring. You release that energy, and the box definitely picks up kinetic energy, and sort of all in sort of this region in here and all in this region right here. The box does have kinetic energy. It's just not of interest to us because it's not what the problem asks for. But when everything is done, I have this hot surface and a block that's stopped. And so I'm trying to account for where that energy must have gone into heating up this surface here or causing this barbecue to happen. Sort of as we're treating in class here, there's going to be a hot surface right there. And I know that's work due to friction, which is force times distance. So I've got the coefficient of friction times the force times the delta d. And it seems like to me I could just solve this for delta d and have my answer.